was basically saved by the bell curve. Brought me up to a pass. I failed initially, but it brought me up to a pass. And I also, even though my plays have been down at Stratford and around the world, I also got the lowest mark in my creative writing class. So when I graduated from university, I didn't think there was too much I could do, and I was babysitting my sister's kids one night, and I came across a book of letters by the American poet Sylvia Plath. It was letters to her mother, and it was clear from the letters that she taught herself to write by sheer determination. So as a teenager, she started memorizing poems, reading everything she could about poetry, and she did something we would rarely tell young writers to do now, because it doesn't seem very creative. But if she liked a poem, she'd write an imitation of the poem, something in the same style or very close. And you could see her early poems were very derivative, but gradually as she understood how poetry worked and developed her craft, her own voice started to come into her poetry, and she became one of the most original poets of the century. So that was a revelation to me at age 21, that you could actually follow a path to develop a skill for something. Until then, I had a very fixed mindset. I thought you had to be born with a gift to do well in any subject, and I would give up very easily. And so from Plath, I learned that you could teach yourself through a series of incremental challenges, and that practice was very important, and that turning to other experts was very important. And all of those things are now very well confirmed by the research in cognitive science. And I'm going to be talking about that today because I think that new research has huge implications for how we teach math, not just in elementary and secondary, but also at colleges. Thank you. So, is this working? Yeah, okay. So, about 20 years ago, after I just finishing my doctorate in math, I decided I wanted to help some local kids, and I started a tutoring club in my apartment. I asked the local principal if she'd send some kids who were struggling in grade 6, and she misunderstood me and cleared out her special ed classes and sent all the most challenged kids in the school down. I remember the first girl arrived at Jump, literally couldn't count by twos in grade 6. She had slurred speech. She said she had never read a chapter book in her life. I found out later that she was testing about a grade 1 level and had MID, which is a mild intellectual challenge. So I had no idea what to do with her, and I began to develop the Jump program to teach her. And 3 years later, she decided to go. She had been at a grade 1 level, but 3 years later, after about an hour of tutoring a week, she decided to go into grade 9 mathematics into the academic stream. And I was terrified. I wasn't sure she could do it. But she not only did it, she skipped a year and finished academic grade 10 in the same year. So I was stunned at how she was able to catch up, and saw that in many other students. And gradually, as Jump grew as a tutoring program, teachers started to invite us to come into the classroom to help them. And that was a big turning point for the program, because as a playwright, when I started volunteering in inner city classrooms, I saw the kids as an audience. And kids will never get more excited than as a group and as an audience. I think we throw away that advantage in the way we teach math, and I'm going to come back to that point. But I saw how excited kids could get when they experienced success together. So we started developing an in-class program, and it was never really my intention. I'm a playwright and mathematician to build a charity, but it just kept taking over my life. So now I do it virtually full-time. And Jump has grown to the point where we now reach about 6% of the Canadian student population from grades K to 8 are using the program as their main classroom program. And we've just been translated into Inuktitut. We're being used in by about 20% of on-reserve Indigenous students in Canada as well, and we're growing fairly quickly. We also have a US program now, as a program in Spain, and I just found out that the Chilean government just started a large randomized controlled trial in Spain that's being overseen by the MIT Poverty Lab, so the program is slowly spreading to other countries. So one thing that's different about Jump, as a charity, we've been able to develop our materials over many, many years and constantly rewrite them because we don't have to make a profit. We can subsidize a lot of our development. And to make sure that what we're doing is actually working and to also constantly improve the program, we've started working with researchers across North America. This is a short list of some of the people we've been working with. And this is very unusual for a program that produces materials for the public schools, because typically programs are adopted. I don't know, how many people here have children in the public or private system? Yeah, so if you've seen the cycle of adoptions, programs are adopted on a mass scale without any testing. Usually, whoever is producing the materials will say, yes, these work, or they're research-based when the research is not that rigorous. And then there'll be mass adoptions across Canada, and teachers will have to live with that for 10 years. And the cycle just keeps going on and on. And in Ontario, you may have seen in the news, but in grade 6, the EQAO scores have been steadily declining for a decade. So last year, only 50% of kids passed the EQAOs in Ontario, which is kind of alarming because it's a pretty good predictor of what you're going to get in the colleges. And nothing seems to change. There's no mechanisms in place to actually bring in evidence-based approaches. So as a charity, that's one of our missions, is to expose teachers and try and get the school system to use evidence-based methods. Whether they're using JUMP or not, that's not the important thing. It's do you have some evidence that what you're adopting is going to work? So one of the most exciting projects we're involved in is with Brent Davis at the University of Calgary. He's the chair of the Math Ed department. So they've been filming teachers in the Calgary district and suburbs for about 6 years now, and keeping track of the student performance. And they found very strong gains in problem solving and conceptual understanding over a 6-year period in these schools. And even more important, they've begun to isolate what teachers need to teach well, or what kind of methods work best. So I'm going to come back to that and talk about that. Tracy Solomon, who's at the bottom of the list there, is a cognitive scientist at the Hospital for Sick Children, and she's run 2 randomized controlled trials so far on JUMP, and in both trials we did better than the control group. And there are almost no programs in North America that have randomized controlled trials, because it's very hard to attribute cause unless you have a control group and you control for all the variables. So I just want to briefly talk about why the research is so important. And when I say research, I'm referring mainly to research in cognitive science. There's some good educational research, but there's a lot of new research in cognitive science that's very rigorous and somewhat counterintuitive. So there's an article by Kaminsky. You can look it up on the internet. Jennifer Kaminsky, where she asked teachers, elementary school teachers, would kids learn better from bar graphs that are made of colorful objects, pictures of objects, like if the problem's about flowers, pictures of flowers stacked up for the bars? Or from gray monochrome bars, just gray bars. So you can probably tell this is a bit of a setup. But what do you think the teachers selected almost universally as the most effective representation for teaching bar graph?
Flowers.
Yeah, flowers. And why? Well, everything, if you attended education college, everything in our training says they're relevant. They're more engaging than the gray bars and prettier. They represent what the problem is about. They're more concrete. All those things are assumed to be always the way you want to go when you're teaching. But surprisingly, the kids learn better from the gray monochrome bars. I don't know if you can think why. Maybe I'll get some audience feedback.
Less distraction.
Yeah, the kids got caught up looking at the petals and so on. They got caught up counting the flowers. They didn't learn to use the scale as well. There are all kinds of distractors in this representation. But, I've seen teachers adopt textbooks in half an hour by flipping through pages, and it's not their fault. Teachers are my heroes, my absolute heroes. JUMP wouldn't exist if teachers hadn't stuck their necks out and used the program. But teachers will admit that they may not be qualified or have time to make a good choice around resources. This is a serious problem, and you're inheriting, I think, a generation of students that have gone through that kind of adoption process. So I'm going to come back to that. That's part of one of the themes today. Cognitive scientists are finding more and more that kids are suffering from cognitive overload when they're learning math. They're just being overwhelmed by too much extraneous information, or ways of representing things that actually obscure the mathematics, and I'm going to give you lots of examples of that. So, as I said, JUMP has participated in some very rigorous studies, but I want to start with just a case study because it says something. I have very radical beliefs about ability based on my own struggles. And so this is a case study we did in Toronto at a school called the Mighton School. The kids were tested at the beginning of grade 5 on a standardized test called the OCMA. And the red bell curve, which we cut off at both ends, just represents the distribution of marks with the same standard deviation and mean. We cut it off at the 9th percentile because the lowest mark was in the 9th percentile, and the highest mark was in the 75th percentile. When we survey teachers, and this, I've observed hundreds and hundreds of schools ranging from the worst inner city schools to the most elite private schools. And universally, teachers will say, yes, we see that difference by grade 5. That would represent about a 3 grade level difference between the bottom and the top. That would be kids as low as a grade 2 coming into the class. And that's one of the questions I want to raise today or ask you to think about. When people talk about improving achievement in math, they usually will talk about shifting the mean higher. But they don't focus too much on the width of the distribution, how wide the bell curve is, and what a difference there is between the top and the bottom. Because I think as a society, we've just accepted that math is an inherently so hard subject, that it's a subject that differentiates kids, that you have to live with that by grade 5. There's nothing you can do about that. You'll always have the high flyers and the strugglers. And, it gets worse as the kids get older, as you've seen probably. By grade 6, I mentioned kids, only 50% are passing the EQAOs, and it's a tragic situation in inner city schools in Ontario, because it's more like 25%. It's an insane social injustice in Ontario. And then the gap just gets wider and wider. So I'm sure you inherit, a generation of students who may have a, 8 grade level difference by college. So this teacher, if you're a parent, we have free online teacher's guides that cover the entire curriculum from kindergarten to grade 8. It's just on the Jump Math website. It's just Jump Math, and when you get to the home page, there's a little link that says create an account. You still have to fill in your information, and you can access all our teacher's guides. And I'll show you what those look like later. Also, if you're teaching, we have a US site. Also, we adapted the program to the Common Core because we think the Common Core is an extremely good curriculum. Apart from all the politics in the US, it's an extraordinary foundation, and it's more advanced than the Canadian curriculum. So if you're teaching, you might want to look at our US site also. Our grade 8 books contain material up to grade 10 in Canada, and our grade 7 books. So you might find if you want to look at different ways of teaching things, you could check out those lessons too. We'll eventually go higher. We're trying to raise money to do high school. And we also did an experimental year with George Brown College where we developed a college entry program. And it went very well, but unfortunately we haven't had the money to finish it. We're hoping to finish it within the next few years. So this teacher followed the online teacher's guides for a year very, very closely, and this is what the bell curve looked like a year later. So this was reported in the New York Times. It was reported in Scientific American Mind. This teacher could reproduce this data. This is real data. It's rather surprising, but the lowest mark was in the 95th percentile. And then a year later, all her kids, after another year with her, were all signed up for the Pythagoras math competition. And 14 of the 17 got awards of distinction, and the other 3 came within a few marks. And 4 of those kids were on special education plans. It was a very, normal class with a lot of wide distribution. So this was a great teacher. She had a lot of advantages. This is a private school where she had a very strong parent community, but she didn't send home homework on purpose because she didn't want the parents messing up the kids or fighting with their kids. The most common, I have a daughter, and I avoided as much as possible teaching her. because it's terrible for a parent to have to teach their kid. And this idea that, that is a great thing to send home homework, I don't know if it's a great idea if you've ever tried to teach your own kid. Because the most common thing they say is, that's not how my teacher showed me. And then you've got a problem. So she didn't send home homework. She had a small class. She had tons of advantages. So you wouldn't expect this kind of shift in a normal classroom. And in fact, we find it very difficult to get teachers to produce this shift, largely because we find all of the training that they've gotten mitigates against this. Almost all the training teachers get, I think, prevent them from seeing these radical shifts. And I'm going to tell you what I mean by that in the course of this talk. But you could imagine if we could even get a shift, something like this, what our society might look like. And I'll come back to that. Now we've seen, that was a private school, we've seen similar shifts in a very different setting in England. We worked for 4 years in the Brixton School District and in very violent schools, and they let us work with the behavioral kids and special ed students for 4 years. And these two graphs show the percent of students considered at grade level coming into the study. And a lot of these kids would have fallen behind even further because they were very challenged. And every year for 4 years, we increased the pass rates to about 60% on the national exams. But the most exciting thing is the teachers reported big changes in behavior. They wrote letters saying that the behavioral kids are reprimanding the other kids because they want to get on with their lesson. They're so excited about showing off in math and being good at math. And then, as I've mentioned, we've been involved in even bigger studies, the 2 randomized controlled trials. But I want to step back, and I'm not going to focus much on JUMP today. I want to talk about the principles of teaching that are now coming to the forefront in cognitive science that I think we stumbled on by accident by being in the trenches and are trying to learn from, because I found these things have really helped my own teaching. So I think there are 4 sort of major mistakes we make in the public system, almost philosophical errors that I think are really holding us back. And the first I would call mistaking the ends for the means. So, everyone wants to produce 21st century learners, problem solvers, kids who are creative and can persevere. But we don't seem to be, I'm sure you've seen in your own colleges, you've got a lot of students coming who never want to see a problem again in their life. We don't seem to be creating a generation of problem solvers. In fact, in the States, things seem to be going backwards in some ways, with less respect for math and science. So the question is, are we starting in the right place? We want to produce 21st century learners, but maybe is that seducing us into starting in the wrong place? So there is a big body of research now in cognitive science around deliberate practice. The person who originated this work his name is Anders Ericsson. If you've read Malcolm Gladwell's book Outliers, I don't know if you've seen that book, but he was the one who the media popularized this idea of the 10,000 hour rule, that you've got to spend 10,000 hours to be good practicing to be good at something. That came out of one of his studies of elite musicians in Germany, where he studied the best musicians and the ones who were just under them. And he looked at how early they started playing, how much time they spent reading music, how much time they spent playing in groups. He found only one thing mattered, really. It was the amount of time they spent practicing. It was the only significant thing that distinguished the best players from the worst. And now more and more research has shown that you just can't become good at anything without practice. And even people who are very good at things, often it comes from hidden practice in their childhood. Like Gladwell talks about Bill Gates or the Beatles. So that's one thing that Ericsson found, is that practice is far more important than people think. And also that many of the characteristics that people thought were innate actually can be developed through deliberate practice, intense practice. And I certainly found that myself. I had no talent as a writer or mathematician, and through intense practice, eventually became competent. And I regret that I wasted so many years, till the age of 21, not knowing that through practice I could develop skills. So I think we need to take account of this research, particularly because Erickson and his colleagues have found that there are some ways of practice that are better than others. So deliberate practice, efficient practice, which he calls deliberate practice, involves setting a goal, pushing yourself slightly outside your comfort zone constantly, not too far or it's not efficient. In his book, he talks about a golfer, a guy who wanted to train himself to be a pro golfer, and he put balls in a ring around a cup and just putt in a circle from that distance endlessly and then move them out a bit more. So deliberate practice means not pushing yourself too far. But Erickson also found that it makes a difference having a coach or an expert helping you. So he said that there are some fields like chess, competitive music, and sports, where over the centuries people have developed very efficient means of practice. I guess it's no accident those fields involve money. And I personally think as an educator we should be looking to those fields to look at what does a deliberate practice look like in those fields, because there's now a century of research showing that you can turn almost anyone into an expert very quickly in those fields if you have a great coach. It's not a matter of innate talent, it's do you have a great coach. So let's look at chess. If you pick up any book of chess, a good book of chess, do they start with the full game of chess? No, they start with usually several pieces and one move. Can you checkmate in one move? Any other means of practice would be terribly inefficient. And that's what the research is showing. You don't learn chess efficiently by playing the full game, which is where you want to get to. That's the end where you want to get to, but not the means to get there. You learn much more efficiently by playing much smaller challenges, mastering those and moving on. And gradually you can increase the level of complexity. But what happens in the brain of these people who do this kind of training, gradually novices begin to develop what psychologists call mental representations. So they can look at a position on the board and see, I'm not even going to make that move because I've seen it before. Or I see a pattern. Grandmasters even talk about seeing lines of force. And it's not, the key thing, it's not that their brains became significantly different from the average brain generally. So they've done studies with grandmasters who can play chess blindfolded. So they obviously can remember anything. But when you put pieces on the board in a random position, they can barely remember that any better than a person off the street. Their memory is so good around chess because they've developed these mental representations. But they can't, their memories didn't become better. They didn't suddenly become superhuman. They developed these mental representations. And they found the same thing in studies everywhere, that also prior knowledge is far more important than people think. So they did a study of physics students at university, and the undergrads were asked to classify problems, a bunch of physics problems, to classify them and put them in groups. And graduate students were asked the same thing. And the undergrads tended to classify the problems according to very superficial features. So they'd say, oh, these are all about inclined planes or about springs. But the graduate students would classify them according to much deeper principles, like these are all about conservation of momentum or energy. So that's one, but I'm not going to stay too long on any of these areas, but that's one area you might want to look at. There is a vast body of literature now suggesting that efficient practice in a much more incremental way that helps people build and practice developing mental representations works far better than playing the full game. And what I'm seeing in the public system is the impetus is always play the full game. So if you've got kids in grade 5 or 6, you know that most classes, teachers are encouraged to start with a rich problem and let kids find their level. They can work in groups and kind of find where they're going to, some of them will do well, some of them will work at a lower level. You can barely get a teacher in Ontario not to teach that way because they've been told over and over again that's the way to teach. But from my perspective, that's kind of like starting with a full game of chess. And it's very hard to argue against because the opposite of a rich problem would be a poor problem. So you can barely escape, you can barely win that argument. So there's another body of research that I mentioned around cognitive overload. This is a great quote. This is one of the best books of education I've ever read. Daniel Willingham, who's a cognitive scientist from the US, he looks at 9 principles that are well established in cognitive science and talks about how they can be applied in the classroom and what the implications are for the classroom. He used to be a creative writer, so he's a fantastic writer. But he says that people are naturally curious, but we're not very good thinkers. And that sounds like a kind of radical claim, but most of what we do is subconscious or automatic. Otherwise, we'd die. Most of the complex things we do. As thinkers, we're not that great as conscious thinkers, and we certainly don't want to work too hard, most of us. So I think you can see that in mathematics with the Roman civilization. Over 7 centuries, even though they built many roads and did many calculations and collected taxes and so on, they never developed the concept of zero. You can't do any kind of efficient division with Roman numerals. They had to do workarounds with abacuses and so on. So that's an entire civilization doing mathematics at a high level that never developed the idea of zero. So the idea that kids are going to discover on their own some of these mathematical principles without guidance is not terribly realistic. And if you're interested, there's tons of research around cognitive overload. So the top study is a meta-analysis that was published in 2011, where they found discovery-based learning only works if it's combined with lots of feedback, worked examples, scaffolding, which means breaking challenges into manageable steps and providing practice, and elicited explanations, which means helping kids explain their work, not expecting them to write long essays. Also, Herb Simon said that, he's a cognitive scientist, said that calling practice drill and kill has done a huge disservice to teachers, because the research is showing, the real research is showing, that's absolutely essential to gaining expertise in any area. He said that, and this is a really important question, it's how do you make practice interesting? So I'll come back to that. So anyway, if you take these two bodies of research around deliberate practice and cognitive overload, and ask, well then how could I design a lesson that takes these things into account? And that's what I want to look at now. I'm going to move away from the theory and do some math with you now. And I want to look at 3 areas. One is the big obsession in the public system now is applied problems, applied multi-step problems, real-world problems. So I want to start there. And then the next thing I want to look at is contest-level problems. Could you actually train students to work at an even higher level on contests? And the third thing I want to look at is just sort of basic operations like division and things like that. How could you teach taking account of some of these principles? So, and I'm also going to move up in grade levels. I'm going to start at grade 3 just to show you the whole spectrum, but I'll end around grade 9. Oh, this is the Kaminsky article I mentioned, called Extraneous Perceptual Information Interferes with Child's Acquisition of Mathematical Knowledge. And her research goes as early as grade 1 now, surprisingly. She found kids learn fraction concepts better from gray and white circles than from colorful pictures. And what are all teachers using? So this is just one example of why the research is so important. So this is a cartoon I love from Keynote. And it's funny, but it's also profound, because we do backflips and bend over backwards trying to make math relevant and engaging for kids. But I think kids can always see that these problems are artificial. I once saw in a textbook for grade 8 kids, the kids had to design a record cover, which sounds really engaging in real world, but they had to put a trapezoid on it that covered 80% of the area. So I don't think any record company executive is going to ask you to do that if you're a band, and so the kids see through that. So what I'm going to argue is that actually, just like mistaking the ends for means, maybe trying to make math relevant to kids is actually shooting ourselves in the foot for many reasons. First of all, because the kids will recognize it's artificial no matter what you do. But also, quite often, it's not just the mathematical complexity of the problem that's causing cognitive overload. It can often be the language. If you look at typical textbooks in elementary school, they're dense with language. So we decided in grade 3 to try a different approach. If kids have part-whole problems in grade 3 where they've got 2 parts that make up a whole, quite often they're misled by the language. So if they see the word more in the word problem, what'll they do? What do they think that? Yeah, they're going to add. But you can create a problem where more means subtract. And just telling kids to look for keywords or underline the information just doesn't work. So we decided to strip the problem down. This is from our student book. It's just so you know, if you ever see a teacher using JUMP, please implore them to put the student book away. It's not a workbook program. Every lesson should be really dynamic with lots of questions, assessment exercises. The workbook is only used to assess at the end of the lesson. A lot of teachers are just Xeroxing jump and throwing the worksheets in front of the kids, which breaks our heart because it's not a workbook program. So anyway, we started with the easiest problem type, which would be the part and the part, and you'll notice, how does that look different from a typical textbook, if as a parent you've ever seen a grade 3 textbook?
No pictures.
Yeah, there's no pictures. What else?
Seems to be the same
No
question.
words.
Yeah, there's very few words. It just says green, blue, 4 green marbles, 6 blue marbles. So in each question, and also, this is very important too, the language never changes. We don't change to rutabagas suddenly in the next question or some other thing. Every time you vary something, you've lost part of the classroom. And the numbers are very small because we can't assume coming into grade 3 class that kids have any fluency whatsoever, especially the lower end of the class. So this levels the playing field, and all kids, I've encountered very few kids who couldn't draw shade in those models. Also, it's semi-concrete. So we don't go straight to the Singapore version of bar where they just have abstract bars, which we get to eventually, but we start by letting the kids shade in the boxes. Then we move to other problem types. They might have the part and the difference, and there's a hard case there where you have fewer than the other person. But eventually the kids have to be able, on these little grids, be able to solve any problem and know any of the combinations of information. And then this is something I'm really proud of. Before we go to word problems, we give the kids charts where they have green marbles, blue, total, and difference. The first line is filled in, but in the other lines they have 2 pieces of information. They have to draw a picture and fill in the rest of the information. So again, there's an equal playing field for all students, including English second language students. No one has any problem reading this. But that doesn't mean you have to be teaching in a rote way. So at the bottom of the page, we have numbers that are bigger than the grid. It's 12 and 35. So the teacher can let the kids struggle at that point and think, what do I do now? They might have to draw a little sketch or use mental math. But these small variations are equivalent to the ones in chess, where you only vary 1 or 2 things at a time, rather than jumping to a new word problem, new language. And then our writers put fragments of word problems into the charts and insisted that the kids have to fill in all 4 pieces of information so they don't guess, which kids naturally want to guess. And then we move to word problems, and then in book 2 we come back to much more complex multi-step problems where the kids are drawing sketches. So anyway, this is something that's testable. I would argue that a class taught by this method would actually end up being much better problem solvers than a class that starts with full, rich problems. And you'd have far more kids coming along for the ride. So now I want to look at contest level problems. You all got some paper there. So this is off the Olympiads for around grade 6 to 8. It's a pretty challenging problem for most kids. If you wouldn't mind humoring me, maybe with a partner, just trying this for a minute and seeing if you can get any of those letters. Every letter is unique, stands for unique number. So if H stands for 5, then no other letter can stand for 5. And you have to figure out what combination of numbers would make that work as an addition. So it would help me if you just worked on that for a minute, because I think some of the things I'm going to say will make more sense. So try that with a partner and see if you can get even any of the letters. Now, you're all math teachers, so you're going to find this much easier than the average teacher. Elementary school teachers really find this very challenging. Yeah, thank you. Yeah, they're all 9 or less. Yeah. Thanks for asking that. So I hate to interrupt your fun, but I don't have any time. The reason I wanted to work on that for a second is that I have radical beliefs, as I said. I think these problems used to freak me out when I was younger, but now I find them pretty easy, and I think there are 3 reasons I find them easy. One is that over the years I've developed strategies, which are very powerful. I have more knowledge than the average person, which plays out. I'm going to show you how that plays out. And I also have a positive mindset. I will never give up. So one of my strategies that I use in my research all the time is just looking for patterns or violations of patterns. Is there any letter there that kind of stands out for you as looking different from the other letters? Yeah, some people say H because there's 3 of them. Is there any other letter that stands out? Yeah, T for me was a T, because it's the only letter that doesn't have anything above it, right? So I'm kind of like a chess player. I've played so many games, when I look at that, things just jump out at me. It's not because I was born with a talent for this thing. Now the second thing, and here is something that people really do not take account of enough. I have more knowledge than most people. So I know what T is without even thinking. Just subconsciously I know what it is because I know something about the structure of addition. When you add a pair of 1-digit numbers, what's the biggest number you're ever going to regroup? If you add 9 plus 9, no matter how often you do it, you're going to just regroup 1 always, right? You add 8, regroup 1. 9, regroup 1. You can't regroup more than 1. It's impossible. So I know T is 1. Just like that, by looking at it. And then, now I know E, because if that's 1 and 1, I know that's 2.
Yeah.
Then I would just start guessing and checking, because O can't be 1 because I used 1 already. It would be nice if I could use 1 again, but I can't. So O is what?
6.
Yeah, 6 and 6 would give you a 2. And then you regroup a 1 up there, and then you could just guess. That's how I did it. You have to guess a long time though, because H is 9. Eventually, a lot of people think that can't possibly work, but they forget there's a 1 on top. People think it's a 0, but that would make that a 0. So it's a 9. So then you can get the rest by using a bit of logic. You've eliminated most of the possibilities, so now S and M can only be a few things. So the only reason I wanted to show you that is because that, if you gave that to a grade 6, 7, 8 class, you'd see a few geniuses get it, and the rest would just give up. But I think you can train students for this. So I'm writing a new book called All Things Being Equal, where I'm trying to argue that we've had trouble solving most of our social problems and eradicating poverty because we've overlooked a deep root cause that no one can see, which I call intellectual poverty or intellectual inequality. And you saw that in Mary Jane's class. That was a private school where parents are paying money to produce a 3-grade level difference. Intellectual poverty cuts across all social classes, and it's invisible. No one would believe you could take a class and turn them into a gifted class within a couple of years. Virtually all the kids or all the kids. So now in my book, there's a chapter where I argue you could also train kids for competitions. So where would you start? I just tested this in Brooklyn the other day. The kids went nuts for it. These were grade 4 kids in a very low inner city school. They would love this. You could start with very simple problems like this, like that, and the kids. And then this is an amazing thing. You just add more digits. The kids think it's harder. They go crazy. They want longer and longer problems. Then you could throw in regrouping, for instance. You could say, well, how in the world could this work? And the kids are puzzled for a minute, then they figure it out. It doesn't look like you can get a 9 from a 2. Sorry, not a 9. Let's say a 3. Because 3 is bigger than 2. So they have to think, that doesn't work, does it? I have to make up a good problem. There you go. So the kids were they loved that because they had to struggle a bit and think about it. And then one of our writers created this sequence. It's just like a chess training book. She created this sequence of problems, which is really beautiful. It's all the different variations on regrouping. Like if you look at the first problem, B plus B could be 2, which would give you 4. But then B has to be different from A, so that can't work because you're not regrouping. Otherwise, A would be 2 also. So you have to. It has to involve regrouping. So B has to be 8. What would it be? 7, because you have to regroup. So if you work your way through those, you train yourself how to get up to the full host-host problem. And here are some bonus questions our writer created. And you're laughing, but I actually broke up a fight once in a school, very violent school, by telling the bully if he didn't apologize, I wouldn't give him this bonus question. Kids go crazy for this stuff when they're not afraid, when they think they can do it. Kids are born with a sense of wonder and curiosity that they lose through failure. I'm going to come back to that. It's the most surprising thing I've seen is how excited kids get about math when they can learn it in a way, the way their brain works. So that's just an example, and I give lots of examples in the book of very hard contest problems where kids with a bit of knowledge and some strategies could solve them. Now, I want to go to the last thing about basic operations. I love this cartoon too. I don't know if you can see it. There's lots of equations, then a miracle occurs. And he says, I think you should be more explicit in step 2. So, I think sometimes when we teach, a miracle just occurs, to the kids anyway. And I saw this in Calgary. I asked about 700 teachers at the Calgary Teachers Convention why, when you divide 7 by 2/3, you're allowed to flip and multiply. And someone yelled out, because you get the right answer. So I've surveyed a lot of teachers from grades 6 to 8, and 7 to 8. And if they have an explanation of this, it's usually pretty complicated. It usually involves reciprocals, multiplying by reciprocals, which at that grade, that would be fine for college because the kids are supposed to know that. But at that grade level, it's not really an explanation because then you have to explain how multiplication works, which is equally mysterious to a lot of teachers. So quite often when I'm training teachers, I'll ask for a volunteer, someone who's really math phobic. I'm afraid I can't find anyone in this room. But maybe someone could pretend they were. And I'll ask you just a couple questions and you'll figure it out yourself. My method is, could I ask someone a couple questions? Okay. So I think one of the most important things is go back to the right level. And the right level for this is grade 3. So suppose you had 6 divided by 2, and you had 6 things. What would that be telling you to do with the 6 things?
You have to split them into 2 groups.
Yeah, okay. And that's correct. And unfortunately, though, if you're in grade 3, some people might have done it differently. Would anyone have split them? Yeah, into groups. Right. So at the back, what's your name?
Sean.
Sean. What is the 2 here?
The number.
Yeah, that's the number of groups. And what's the 2 here?
Size.
Yeah, the size of the group. And kids in grade 3 get very confused by this, and often the approaches that are being used don't help them. So we did the same chart method in JUMP, where we would give them fragments of word problems, and they'd have to tell us how many objects in total, how many in each group, and how many groups, until they nailed that. Then go to the word problems. Because if you switch back and forth between word problem types, hoping that they'll know what you're talking about, it's almost impossible for grade 3 kids. Because that's ambiguous. You do not know what the 2 means unless you have a model or an interpretation. So at the grade 7, 8 level, I find that it's easiest to start with the size model. For kids, it's a bit harder for them to understand half a set. So you could take the 6 sticks and turn them into a chocolate bar, because kids really understand that. You could even make a number line. And you could point out to the students, well, 6 divided by 2, remember the size model, that would be like getting 2 pieces in each group. And so there'd be 3 groups. So, but this isn't telling you to take a piece of size 2. It's taking you size. A lot of people think that means give me half the chocolate bar. That's the most common mistake adults make. But it's telling you to give me pieces of size a half. So Sean, I know you're a math teacher, but could you tell me how many halves you could get into one piece there?
I think you get 2.
Oh, amazing. Brilliant, Sean. And without me even drawing it, could you tell me how many in the whole chocolate bars?
2, 4, 6, 8, 10, 12.
Oh, Sean, you're so impressive. Okay, Sean, what if I made it thirds now? How many thirds could I get into here?
Oh, 6, 9.
Oh, you're showing off now. You're telling me the whole answer. I just want to know how many.
Oh, sorry, 3.
Okay, Sean, now you're in big trouble. I'm going to have to do what I can't even draw. You're so brilliant. I'm going to have to, let me see if I can make it hard. There. So, Sean, are you noticing a pattern here with what you're doing? What would you do?
So it seems like every time you change the bottom number, there's that many pieces.
That's right. That's right. Very articulate, Sean. Are you sure you're grade 6? So what would you do with these two numbers?
Well, I was counting by 106 times.
Yeah, right.
Instead of multiplying.
Yeah, brilliant. So you can imagine in a grade 7 class how excited the students get. And the kids are very naive in grade 7 and 8. They think that's harder. They love these kind of challenges. That's how I got the bullies who apologize. They love these kind of bonus questions. So eventually the kids see why you multiply and why that would flip. Now the next level, and I don't have time to do this properly today, but the next thing would be to look at fractions where the top isn't a 1. And so there I tell students, the other thing about jump is we assess continuously. The research is showing you have to assess constantly, minute by minute. So if you were in my class, I'd give a test now, and I wouldn't move on until I had 100% mastery, until all of you were able to split up the chocolate bar and show me why the rule works. So next, what I would suggest is you ignore the 2 and cut the chocolate bar into thirds. Just make it a third, cut the whole thing up, and then I ask students, is 2/3 bigger or smaller? Or another thing I'll say is, if this is a third, how could you make 2/3? And it's important that students know that the order doesn't matter. You could glue any 2 back together to get 2/3. Because prior knowledge is really important. I'm very sensitive about prior knowledge and how it gets in the way. When I used to teach this to adults, I was really surprised because I'd say, look, I start grouping the thirds back into 2/3. Where do you think many adults will go to get the next 2/3? Yeah, they'll go to the next whole number. Because they're so used to seeing fractions start at whole numbers that they're shocked that you could actually group it this way. But kids wouldn't leave out any chocolate. I mean, they would take the whole thing. So eventually, if you group them, you get 9 of these things. And you can start to see why the rule works. You flip that and multiply because there's 18 thirds in the whole chocolate bar, but you divide by 2 because you're putting them back into groups of 2. The last thing you have to worry about, I don't have a lot of time, but maybe it's just the remainder. If you look at this case, and you use the rule, you get this, which equals 4.5, or 9/2. And if you draw a picture with the thirds, well, there's one of the 2/3. There's the next one. There's the next one. There's the next one. So I can see 4 in that picture. There's 4 2/3. But what is this thing on the end? It says a half here, but that's not a half left over. That's a third left over. Why would my answer tell me a half? That's what a lot of adults don't understand what that remainder means. They think that means half a piece of chocolate. It doesn't mean half a piece of chocolate. It's a third of a piece. What's that a half of? Go back to the original question. What is this a half of? It's half of this thing that you're dividing by. It's half of the 2/3. That remainder is relative to what you're dividing by. It's a half of that thing. So I'm sorry I rushed through that. Again, if you were my class, this would have taken a lot longer. I would have given assessments. But that's the only other thing you really have to teach for kids to understand this in a fair amount of depth, because they don't understand what the remainder means. Now, I think you are suffering probably from this idea that mastery is rote. Mastery and practice are just rote things. So what really matters is problem solving. But I've tried to suggest that those are deeply entwined with problem solving. A grade 7 teacher once told me a story that shows how the idea of mastery has gone from our schools. He said he saw a very intelligent girl measuring with a ruler in grade 7. And sometimes when she was measuring, she would line up the 0, with the end of the object, as you're supposed to do. But sometimes she'd line up the 1 with the end of the object, just at random. And he said, why are you changing what you're measuring from? And she said, well, on my ruler, under the 0, it says millimeters. And under the 1, it says centimeters. So if I want to measure in millimeters, I line up the 0. If I want to measure in centimeters, I line up the 1, because it says that underneath. You know, and that girl had gotten to grade 7 without, and I'm sure you're seeing kids getting to high school with no times tables, no understanding of fractions, to university or college. So the same thing with any form of division, like long division. I don't know if you've seen students struggle with this. There's many different models of long division, but the traditional algorithm you can teach also we call the method of jump structured inquiry. Kids are figuring things out themselves all the time through questions. The teacher tells the kids almost nothing, but the inquiry is structured so everyone gets it. So here you could tell students that's 3 friends, one model would be 3 friends want to share 7 dimes and 2 pennies. Then I'd assess to make sure everybody got that, and then I'd ask students to draw a picture of the dimes. Just divide up the dimes. So you could draw 3 circles for the 3 friends, put the dimes in one at a time. And I've taught this in multiple grade 4 classes, grade 5 classes. No one has any trouble doing that. The only thing that sometimes they have to have practice not putting that last one in. Then you can really ramp up the inquiry. You can say, look, you see adults doing this. Where do you see those numbers in my picture? So where do you see that 2 in this picture? Hopefully you see every friend got 2 dimes. Where do you see the 6? You gave away 6 dimes, and the 1 is the remainder. So again, you assess, and kids can draw the picture, put the numbers in, and understand what it means. And then you could take some play money. You could say, look, there's still a dime left over and 2 pennies. And you can pretend to be dumb, and you can give one kid a dime, one a penny, and one a penny, and say, there, I divided up the rest of the money. And the kids always protest and say, no, you should have regrouped that dime as 10 pennies. So you have 12 pennies, and then you divide them up. And that's what this mysterious bring down step is that no adults understand. When you bring that 2 down, you're regrouping the 1 as pennies. You're grouping the bigger unit. So the tragedy for me as a mathematician who spent years doing this is I think math is a really trivial subject in many ways. Even problem solving is taught well. And we're trying to convince teachers that math is a gift to you. It's not actually the hardest subject in public school. It's not the subject that should be differentiating kids. It's a subject where all kids could succeed at roughly the same level as they did in Mary Jane's class. It's a class where they could actually feel what Durkheim called collective effervescence. They could all feel excitement together. So that's the final thing I want to just mention. Not only are kids more alike cognitively, the way they learn, but they're also more alike in what motivates them. So I find we vary too many things when we're teaching. So here's an example. If kids could add fractions with the same denominator, how could you make harder questions? Well, one is just make the denominator bigger. Kids in grade 5 fall for that. They think bigger denominator, harder question. Or you could add another fraction on the end. You could throw in a different operation. You could make an algebraic puzzle. Or this bottom one is at a different level. Kids say, you didn't teach us to teach fractions with the same denominator, but if you regroup those fractions, a third goes with 2/3, and you can actually get all ones. So we're trying to train teachers to vary less and keep faster kids occupied with smaller variations. And then what happens is the weaker kids start speeding up so they can get their bonus questions. So in the research on motivation, people have found that people are motivated by a sense of purpose, mastery, and autonomy. And in a class where everyone's mastering everything and expected to master everything, kids get so excited at meeting a series of challenges. They also feel a sense of purpose because everyone is succeeding together. In a class where not everyone is succeeding, you're saying either the subject isn't important enough for me to teach you all, or you can't all learn. There's only downsides in a class where not everyone is mastering. And finally, kids start to, this is unbelievable, but they will ask to write their tests. We've seen in some of our studies. they will beg for the bonus questions. They begin to feel that they're making a choice because it's intrinsically motivating. Finally, Carol Dweck, who wrote the book Mindset, is a fan of JUMP. There's a video of her on our homepage saying that because we keep kids in a zone where they're doing things that look hard but aren't too hard, that would help them develop growth mindsets. And I'm going to wrap up now. If you're interested, you can go, this is what our teacher's guides look like. They're all free online on our website. If you do ever need the student book, you can order them. That's the only thing that sustains us as a charity is the student book. But these lesson plans, you might find them useful in your own lessons. Check the US site. They all have extension questions that are much harder questions. If you're only using a student workbook, you're not getting the conceptual heart of JUMP. We also have smartboard versions of the lessons that have interactivity and help teachers teach the lessons. If you're interested in some of this research, if you give me your card afterwards, I can send you an article I wrote for Scientific American Mind that summarizes some of the new research. Sorry I'm rushing, but I have to conclude now. And yeah, so that's the article and the website. I'm happy to send it. And this is just a classroom where math is being taught with a real sense of joy. And there's not only an economic loss to our society from having an innumerate population, but you cannot believe how excited kids get when they're allowed to meet a series of challenges in a group where everyone's succeeding together. It's magical, and for me that's the deepest loss. The kids are born with a sense of wonder and curiosity, and they gradually lose that over time. People think it's strange that I'm a mathematician and playwright, as if if you're using one half of your brain, you have to leave the other half empty for storage. But that's just a myth. Like, why can't kids have a choice? Why can't they be brought through high school loving every subject and feeling they could choose, maybe even more than one career? So that's what we're working towards as a charity. And we would like to produce a college program, and we have one that's almost finished. So if there are places that want to test it, maybe give me your card too, because we'd like to finish off our college entry program. So thanks so much. It was really a pleasure talking to you. Okay, great. So I should take questions here.
Okay, so we actually have built in a question time period into this session, and I'm sure you have lots of them. And also probably a lot of people want to know what the O, the S, and the M are if they haven't figured it out. But before we get to that, because I know there will be lots of questions, I do want to formally thank John for coming up to Aurelia. And joining us on this wonderful day, giving us wonderful tools that on the surface of it, you think, how can that be a tool? This is research, this is in theory, but it has shown us that those tools, they can be put into practice very, very easily and very concretely. And yes, it is developed for grade school level, but I know definitely students taking integral calculus can use them at the same time, and definitely those of you in upgrading courses can use them at the same time. So thank you very much on behalf of the OCMA.
Thank you so much.
And we will open up to questions. Okay. So I will
Take the mic around.
I will wander.
John, our first year college students, even when they have to add two simple fractions, will pull out their calculator. What is your opinion about calculators?
Well, for elementary school teachers, it's a complicated question. I mean, calculators are okay for doing some explorations, or if you don't want kids getting exhausted doing long calculations when they're not that important. Or you might have a really challenged kids who you let use a calculator. But there are ways to teach the times tables. I did a TEDx talk that's on our website if you want to look at that. But here's an example. There's no reason kids in grade 3 shouldn't know all the times tables, for instance. So if you just put this pattern up to your students and say, what pattern did you see here? So kids, I taught this in a grade 3 ICT class, a special ed class in Brooklyn, and the kids went for 90 minutes. They were so excited about these patterns. The teacher said, we've never seen them work this hard. So what patterns do you see there? You know, most people see the vertical patterns, but if you look across, do you see any repetitions? You look across, you'll notice that the first and last, which is very good news because it means that what you're multiplying by is the ones digit of your answer when you multiply 6 by an even number. And what's the relationship between the ones and the tens?
To increase.
Yeah, this is doubling or halving. So a kid can remember that in a chunk. They don't have to memorize a bunch of disconnected facts. And so if you're interested in this, if you have your own kids, our grade 3 US book and our grade 3 Canadian book have multiple lessons showing these patterns, and my TEDx talk shows some of them. That's just one example. There's no reason kids can't practice. Remember Herb Simon said, how do you make practice fun? This is how you make practice fun. Kids feel a sense of ownership, that they discovered these things, and they remember them better. So it's insane that we have kids entering high school without knowing their times tables, or that they're relying on calculators for those things. It's insane because not only does it slow them down, but the research is suggesting they'll never see a pattern or make a generalization or an estimate or see a connection. They're hobbled as problem solvers. The idea that you're giving them lots of rich problems, that's like throwing gasoline on the fire if they actually don't have the basic strategies and skills. If you have an entry-level sort of remedial program at your college, look on our website. We have a level D confidence builder. They're free. You can just download it. So it's a confidence building unit. It's on fractions, and it's a crash course on adding fractions. And we developed it so kids, I've taught it to grade 3 classes because all the denominators on the easy pages divide by 2, 3, or 5. So the kids don't need deep number skills to do this. But they come out thinking they can do anything with fractions. And we've had miraculous results like in Brixton where the kids thought they were just geniuses because they could do all this fraction work. So you might look at that and try it with some of your kids, even for a few days. It's pretty long, you might cut it down. But at any level, and this works for teachers too, if they see they can do it in something that looks hard, that has a big effect on the rest of their learning trajectory. But calculators are disastrous when they prevent kids from getting basic knowledge.
I probably have teacher voice. I did my master's work with Brent Davis on fractions, a concept study on fractions at U of C.
He's fantastic.
But one of the things that I came across often was that whole prior knowledge thing, that elementary teachers tend to tell their students that, when you're adding, you get a bigger number. When you're subtracting, you get a smaller number. When you're dividing, you get a smaller number. And so that's embedded in their ideas about division. And then they get to grade 4 and they start dividing by fractions, and then they're thinking, wait, what? And it screws them up. And so we think we're helping them by giving them an erroneous pattern.
Yeah, I agree that with all the things I talked about today, you have to keep circling back and going deeper and deeper. Even our fractions unit, we've gotten a lot of trouble from this unit because it's fairly mechanical. We wrote it just as a commons builder. It's not a deep look. The kids do see with fractions, with pictures, why the rules work, but it's not deep. And you have to keep coming back with our regular materials. But there is a place for this kind of more superficial approach to things to give kids a sense of mastery too. But I agree with you that around grades 6, 7, 8, they have to learn deep. They have to learn that there are many multiple metaphors for multiplication and division. It's not always just getting bigger. Any more?
Yes. How much of this is performance-based versus just coming from the book? You have a great book, a great resource, but the way you teach it, it makes a big difference. And I guess assuming that is a big component of it, and how do we learn to teach that?
Yeah, that's $1 million question that we're struggling with now. As a charity, almost all our resources went into developing the lesson plans, which are like scripts almost. They're like, sometimes they even say this, ask this, here's your exercise. But what Brent found in his research is that, so he looked at two teachers. One got a percentage point gain on these problem-solving skills. One got 0, and they were both using jump. And there were 3 differences in their performance. So one really understood the scaffolding of the lesson. Teachers have to leave stuff out of our lessons because there's too much. But one would leave stuff out in the middle of the lesson, just skip to. She would try and cover stuff. She'd just cover, and so she had to race through stuff. The other made sure she really respected the scaffolding. So the second difference is that one would be assessing constantly. The kids all had little whiteboards that they'd be writing on. Every minute, the teacher would put up an exercise. She'd talk for a minute, there'd be an exercise. And she would circulate or watch the kids, and she wouldn't move on until, she'd slow down if she had to. She'd modify her lesson if the majority of kids weren't getting it. And that didn't mean she was marking everybody, but she just had to keep her eye on a few kids because the steps were easy enough. So that was the second big difference, is one would assess constantly and modify what she was doing minute by minute. The third thing was, it's pretty unique to jump, is one would always give bonus questions. The other didn't. And that's the key to jump, is the kids get so excited. And teachers, when they think of a bonus question, they think it's got to be harder, it's got to have new concepts, new vocabulary. That's the big mistake we're finding is, like I said, kids can do this. Teachers immediately want to go to something just far afield, but I've seen kids in grade 6 jump out of their seats when I did this. They think that's hard. I mean, that's the same question. But the kids in grade 6 go ooh, ooh, like that. So training teachers to vary less and to get excited at their students' successes and to put up bonus questions that are only incremental variations. Another example in that problem-solving lesson I showed, the hardest problem type when you have a part whole problems is when you give the total and the difference. So if I said I've got 20 marbles, I've got 4 more green marbles than blue. Kids have to, I don't even know what the answer is. I'd have to draw a sketch or guess and check. That's a perfect bonus question because you don't have to go teach those faster kids. The second reason is, and you can actually spend your time with the kids who need it, the second reason it's perfect is because if you do that often enough, the weaker ones start speeding up to get the bonus questions. It's uncanny. That's how Mary Jane was able to get such a radical shift. She relentlessly made the kids feel equal. Now, of course, that gets harder the older they get, but I think you can use some elements of this in any lesson. There's a grade 12 chemistry teacher in Vancouver who decided to take her whole chemistry curriculum and turn it into minute-by-minute assessments and teach to mastery, and she got way better results just by. And that doesn't mean more marking because you're barely marking when you're assessing minute by minute. I hope that makes some sense. Of course, I understand that it's way harder to do at college because the gap is just bigger. But I'll give you an example from university. I had a prof who spoke so quickly, we might have been Xerox machines. I mean, we would just be writing like crazy the whole lesson and could barely understand what was being said. It would have been better if he'd just given us a fraction of the lesson and done it well through inquiry and structured inquiry with lots of assessment, made us all feel we got it, and then give us the notes for the rest of the lesson. And then we'd be motivated to go home and do it. Like, I think we've got to start thinking about, are we treating kids as Xerox machines, or are we really engaging them deeply in the process of learning? And I think you can have the best of both worlds. You can have inquiry, but it can be heavily guided and scaffolded, so it almost looks rote. You can have both together.
Very nice. We do have the basic level, but we do have the thing, and whatever you said, it's very, very interesting, very helpful for all of us.
Oh, good.
Lessons we do have, yeah.
Oh, good.
And students do find traction, especially hard to understand. And I can see many of what you said working very well in the courses.
Yeah, I've taught a lot of high school math right up into university courses. And I find that a lot of the high school math is almost a machine could do it. So much high school math is about definitions and expanding and contracting terms and so on. And even the problem-solving high school usually falls into very fixed categories and types that kids can learn. It's almost harder to solve problems in elementary school because you've got so many different problem types. What kills kids, I've found, is I can teach that to anybody. It's when they deal with a number, like a fraction, or simple algebra, or ratio, percent, or integers. That's what kills them. And so you almost would want to do a crash course of a couple of weeks coming into university on the grade 8 stuff they missed. And that would almost be enough to close a big part of the gap. Also, Professor Daria Barr at the University of Manitoba taught an entry-level course for nursing students at the university, and she had a group of Indigenous students who in the previous year their average mark was a D+, so she did a 1-week crash course using jump materials in the summer. The average mark was a B+ for these kids, and that's how much of a difference a week made for these students. So, to make your lives easier, you might want to see if there could be something put in place like that. And maybe you have that already.
I just have a question. So around something like this to do at the college level, a question around the difference in numeracy and mathematics. So I heard you mention enumerate. And it's something I've been struggling with, and I don't know if you folks have done some thinking about that and say, what would be the learning content for an adult numeracy, which is something that we work with. Because some of these things, definitely we don't need our students to do that are in the high school curriculum, but we definitely need them to be numerate.
Yeah.
And now what is that? What is the learning content, the content?
Exactly the things I mentioned, fractions, and especially percents and proportions. So I'll give you an example. A very famous politician in the U.S., who will go unnamed, when he was campaigning, said that he claimed that 95 million Americans were out of work looking for jobs. So, I know the population of the U.S. is about 300 million, more than that, and that's close to 100 million. So an adult should be able to do this kind of check to see if that's plausible. And I expect that only 200 million are actually working age. So that person was claiming that half of Americans were out of work looking for jobs. And no media let's call them on it. Nobody, almost nobody, no one noticed it. That should disqualify you for the highest position in the land. So, that's just insane. And so I think adults could easily be taught, and it also goes for doctors. If you get a false negative for breast cancer, they did a study where doctors estimated that your odds of dying were anywhere between 10% and 90%. The real odds were 10% because the doctors hadn't taken into account of the huge population of people who test positive who don't have. It's a very big population. You have to look at both parts of the population. You can't just assume you test positive and have it. You also have to assume you test positive and don't have it. And when you look at the bigger population, your odds are only 10%. So a simple course in ratios and percent would go a long way to changing our politics. Basic algebra. One thing I could mention too is even in more abstract class, I don't know if you've ever taught elimination of variables with equations like this, simultaneous equations. I don't know how many people teach this. Something like that. What I found is just start with this exercise. Kids confuse the integer rule. So I just said, look, you're playing for money. You're losing money, you're gaining money. Is that a good day or a bad day? And I said, don't give me the answer because you're just going to guess. So they said it's a bad day, so I say write a negative sign. When they got perfect on that, I allowed them to actually do the subtraction. So in my classes, the kids have to count up something. Then I put strings together and I say, now suppose you're playing over and over. What would you do there? The kids say, we put all our losses together and then all our gains, and then they do that. Then you throw a variable beside it. And then you go to these questions, but you only give them questions like this, where they're just asked to add. Then, when they've mastered, just tons of that, when they've mastered that, tell them to subtract by changing the sign of lower and adding. Then give them a sheet of these things and just say, circle the one place where the variable is the same, where the coefficient is the same. Just identify that, and right over top, if the signs are different, that you're going to add. If they're the same, you're going to subtract. And then they're perfect at this because they've done this work. They're perfect at this. So this is trivial. I've done this with grade 10 classes and had 100% mastery. But if I teach two things at once, I'm down to 70% mastery. Three things at once, down to 40% mastery. If I'm not teaching to mastery and assessing and avoiding cognitive overload, so these techniques can be applied even in college classes. Now, I know it's way harder, and you've got way more to cover, but you can experiment to see if it helps.
Well, thank you very much, John. We have run out of time. But luckily, John will be staying around for a little bit, so he will be part of our cafe. If you have any extra questions, you're very welcome to see. So thank you very much.